so somehow I forgot the ending. The ending is this is the function, okay, and we're trying to compute or first estimate, approximate, and then by limited value the volume under that surface, but really the Excel connects those dots. You can see those dots. Each of these points is, so the x and y are there, okay, and then this value each is the height, okay. So in other words, it's every point here is a three-dimensional point in three-dimensional space, okay. But then Excel connects it into a sphere as much as it could, including the missing data fields with zeros, okay. So, but really, what we're dealing with here is to compute the volume, which is much easier to show than to say, and that is just change the chart type, and here it is. Okay, maybe just the wrong angle. Let me try. What the? I don't think this is. Okay, that's not the right one. Here it is. No. Okay, let's try to start over. It's just all the varieties of Excel. Here it is. Okay. There. Okay, so that is what we're doing. Okay, so just to make sure that the surface doesn't cover our actual computations and the essential steps that we make, we build these bars. We're not just looking at the graph of the function, which is a surface which you have been doing a while. Now we are computing the volume, and the volume is made of these bars. So as you can see, you can actually see it. You see, I clicked on this part of the data, which gives you a row of bars over there, and it corresponds to a row of numbers over there. Okay. So similarly, I probably could not go the other way, unfortunately, but at least I could try to show just rotate it a little bit, so to confirm that it makes sense. Okay, so from above, that's not a rotation. Okay, we can look from below actually. It's interesting. And this is from above. Okay, so that's the thing. This is exactly what the construction does. Every row also is visible as a row of bars. Okay. Okay, now we are moving on to more algebraic interpretation or treatment of this. So at the end, aiming for something like this, we already had in calculus 1 and 2, and so through limits. But it has to be carefully set up. Fortunately, everything is very, very similar. So if you more or less understand what happens in dimension 1, then and with the areas, then the dimension 2 should not have any trouble. It's just more cumbersome though. So to remind you about the dimension 1 Riemann integration, or rather Riemann integral of a function. So how it works out: you have y equal f of x. You have you have an integral. Okay, so you integrate over this integral some kind of function. Okay, y equal f of x. Okay, so we cut the piece of the graph. Okay, now so that's what we are after this area under the graph. You remember that. Now what actually happens is we introduced what's called a partition of the integral AB. Okay, which is simply a bunch of numbers that are usually equally spaced but don't have to be. So n integrals into a partition of the integral AB into n integrals of x, k, xk plus 1. Okay, so then A is x naught, B is xn, and then between them lie these x1, x, n minus 1 locations. As many as necessary. So n is the parameter, and then over that n we have a limit. So xk plus 1 minus xk is naturally equal to b minus a over n if they are equal length. They don't have to be. And then what? Okay, so that creates the nothing but the bases of those bars. So bases of those bars now are created, but where do the heights come from? So these are bases of the bars. And now in addition, so it's number 1. Number 2 is heights. The choice of heights is frequently very obvious. It is left and right hand, but generally speaking, that's what I have to do. Unlike the way we did yesterday, with it was just pretty much it was chosen, I believe, over here in the was chosen to be the right hand. Right hand, yes. Okay, so so heights are the values of the function of f at the sample points. So we sample our function at each of the intervals. So it will be, say, S1, Sn, Sn, S1, Sn, sample points, Sk in xk plus 1 of the intervals. So we place them in an arbitrary fashion, pretty much, within each of the intervals, right hand, middle point, doesn't matter. So this is x1, so that's a c1, s1, s2, sn over here. So n of them. Okay, and then so then that's what I just said. The values are the heights of the values, and so they are f of s sub k. Okay, so then we're moving on to the areas. Each of the area is then f sub k times delta x. Once again, assuming it's the same length, and the areas are these, and then total area is the sum over k, f of sk times delta x, and that is there we are, the Riemann sum. Okay, so looks familiar. Okay, so all right, and then you take the limit. Okay, so really uncomplicated to make that step from the Riemann sum to Riemann integral. You take the limit of this. So limit of the sum came from 1 to n, f of sk, delta x, k, and going to infinity is the Riemann integral, f dx from a to b. Okay, so Riemann integral. Okay, and that's the whole story. Just to refresh your memory, what the difficulty of this plan, and just to justify what you've seen else afterwards, later in calculus 2. So the difference in calculus 1 and calculus 2 is how you compute limits. And I just in calculus 1, I just in the other class I'm teaching, so I'm going to show you. Just to refresh your memory how it works, how you end up computing this whole thing. This is a very short plan, but it's really not uncomplicated in practical terms. Here it is. So the function is 1 minus x squared. How do we find the area? We subdivide. N is arbitrary. In this particular case, I choose left-hand points. And then this is what I end up with. The function is very, very simple, but then you end up with a sum or with the dot, dot, dot. So it might remind you of what's calculus 2, right? But ultimately, you have to simplify this expression for this particular function. So each step 1 over n, you simplify the expression, and then that's where we are right now. Well, we reach this point. So this is summation. Each of these terms represents the area of those one of those bars. And then through simplification, that's where we have arrived. And you remember what happens next?
Oh, we appeal to, there's some kind of summation formula for this.
That's right. Summation formula, the finite sums formula. This one is so 1 squared plus 2 squared plus n minus 1 squared. There's a formula for it, and then so to eliminate dot dot dot, you need that. Why? Because you need to compute the limit. You cannot compute the limit when each of the you have infinity. The number of terms goes to infinity, while every one of the terms goes to 0. So that's kind of thing we cannot handle. So the only way to do it is to convert this formula into a compact single formula, and then take the limit of it. Okay, so that's how it ends, and that is very cumbersome, and certainly was done at some point. And then you introduce the fundamental theorem is what solves this problem, so you don't have to compute integrals in that fashion anymore. So we proceeded pretty much according to the same plan. We're just going to be working primarily in 2 and then high dimensions. Okay, so that's we're not doing this. So it's then we might remember also the function is called integrable. If this exists, if this limit exists, but actually the limit, the integrability definition involves all arbitrary partitions. Okay, all arbitrary partitions should produce the same limit. So if they do not, then the function is not integral. Either one of the limit does not exist, or maybe they do, but not equal to each other. So fortunately, the answer is the simplified answer is pick continuous functions. So continuous are integrable. So and in fact, not only they are integrable, one limit suffices. One limit. This limit, this particular limit. So you pick left hand, compute, and you're done. Or right hand and compute, it should be the same result. Okay, so then once again, that's going to be useful. Now, okay, so what do we do different in dimension 2? Everything is very similar, except now we're gonna just like in that spreadsheet, we have 2 partitions for the x axis and for the y axis. So let me go through this very similar plan. So what the graph looks like, and once again, as I said, we have an integral along the x-axis, and we have another integral along the y-axis, C and D. And then we have our rectangle, which defines my domain. So that's the domain. And then the function, as always, looks like a graph. Looks like a surface. But then, and that might be extended in all directions, but what we do in reality is we cut a piece of it from vertically, so built like a box or like walls, right, rising from this rectangle, and it cuts out some kind of piece of the graph from the graph. So smaller surface, okay, like this. Okay, so then this then becomes our target. So we want to find this volume. All the caveats or enhancement rather apply from calculus 1. For example, if the part of the graph lies below the axis, below the xy plane rather, it will count as negative. Okay, so things like that will appear. For example, remember that is so area could be negative, and now volumes could be negative as well. Because why is that? Well, if you look at the sum right here. The sum works, the Riemann sum works, so why limit our attention only to positive areas? So the areas could be negative, and if we're talking about applications, then when your function represents velocity, and then velocity might be negative, and then your integral is the displacement, and the displacement might be negative if you're going in the opposite direction. Okay. So this one is certainly different, but you never know what you're gonna, where you sort of the sea level is. So once again, we want to take that make that possible. The areas to be negative. Okay, so as I said, it looks slightly more complicated. So I'm gonna have a separate picture for my axes for the independent axes. So also once again AB and CD, and totally separate partitions. So two partition, a partition of AB, and a sample. Well, no, that's just a partition. AB. So it means that A is equal to x naught, less than or equal to x1. Xn is equal to B. Xk plus 1 minus xk, which is delta x, is equal to B minus A over n. Okay, so that is all familiar. I'm repeating exactly what we just had a minute ago. Okay, just a partition of AB. Now we have a partition of CD for Y. Okay, so it will be C equal to Y naught, less than or equal to Y1, and Yn is equal to D. So as you can see, I choose the same number of intervals just for convenience, even though once again it does not have to be the same. So this is x1, x2, dot dot dot. This is y1, y2, dot dot dot. Okay, now the two partitions taken together, they create a partition of the rectangle. Okay, then we have a partition of the rectangle. Let me give you this in R equal to AB cross CD. Okay, so that rectangle, that we have it here, and now we have it here as well, like this. So it has been partitioned into rectangles proportionally, like this. Okay, so also then every rectangle is well, how many rectangles? How many rectangles? How many?
N minus 1 squared? N squared?
No, n squared. Well, yeah, n each, so n squared. Okay, so every rectangle in the x-axis, say here, can be combined with another one on the y-axis, maybe this one. Okay, and then so together they give me this rectangle. Okay, so that's a partition. These are the bases. Of the bars. Of the bars, yes. So they're standing bars, and once again, what we need then, what's missing is the heights. So that's number one. Number two, the heights are, just as last time, heights are the values of the function. At where? At sample points. Of f at the sample points. I don't think I ever wrote that this is a function y equal f of z equal to f of x1. Okay, so Okay, so and sample points. How many sample points? One per rectangle. So n squared of them. And they are indexed. So once again, I'm putting a point here in the middle, not in the middle, somewhere within each of the rectangles, and then I need to find I find the height by going up to the surface, our function, right? So this is the function. So that's how I find a function. Just like in dimension 1, we would go from the sample points in the interval and go until we cross the graph of the function, which is a curve. Now it's a surface, but everything is the same, pretty much. So, and that becomes the height. So it will be, except the only thing that the tricky, you have to design a way to keep record of those partitions, of those sample points, and they are double indexed points. Say S, how should I put it? Sij. Sij in that interval xi plus 1 cross yj plus 1. Okay, so once again, this is the x. Okay, so and the other one is the y. This is the y. So each rectangle within this partition will have a point in it. Okay, somewhere. Just like in dimension 1, the location should not matter, should not affect the answer. That's the point. That's what makes the function integrable. Okay. All right. So then the bases. Okay. So I didn't say what the bases of the bars, and so what's gonna matter are the areas, and the areas are delta x times delta y, denoted by delta a. So the increment of x times the increment of y gives you the increment of the area. Okay. So and then the heights are f of s I j. Okay, so we just write it out. So the areas, the volumes of the bars are f s I sub I j times delta a. So just remember what delta A is. It's just the area of the rectangle. Okay. And then the total volume is the sum of these. It is double indexed, so I will put two sums here. So I runs from 1 to n, and j runs from 1 to n. So remember, I corresponds to x, y corresponds to 1. So this is the Riemann sum of f over r, the rectangle, with an and intervals, I suppose. So n intervals in either x or y, which gives me n squared rectangles. And then the last step is, so once again, another very similar thing is the Riemann integral. If the limit of all the Riemann sums and n goes to infinity. And the notation is a double integral. As you can see, so the rest is very similar. In fact, let me skip the variables. The notation is a bit, looks a bit strange, but if you remember, it doesn't look as strange if you remember where it comes from. Okay, so so if we just try to deconstruct this this notation, then is well, the two integrals come from not only two dimensions but only those two sigma signs. So just like in Riemann integral dimension 1, the integral sign, it is stretched letter S. S stands for summation. So we have now two summations, two stretched letters S, and we have double integral. Now, we do not indicate limits anymore, even though we were going to eventually arrive to that point when we deal with this. But this notation is beneficial in the sense that later on we will be able to also deal with regions not necessarily rectangular. So this is certainly is the example of where it was hard to avoid to have the region where the function is defined to be other than the rectangle. Okay, so I have to actually go around and delete those extra values in order to be able to carry out the computation. It's not really that hard to handle arbitrary domains of the integral. So you just put, suppose my domain is a circle, so what do? I create a bigger rectangle and just fill the rest of it with zeros. Okay, so and then I use the definition that we already have, so which will add zero values in those corners where the function is undefined. Undefined or just lies outside of the region. And then dA, yeah?
I was just curious, when we have a double summation sign like that, is that telling us to first sum one and then the other, or is it telling us to do both at the same time, or it doesn't matter?
Well, it doesn't. Well, you look at the picture. We're adding the volumes of these bars. Doesn't matter. We go this way, that way, or we're doing it at random. That doesn't make any difference. So that's the good news. Okay. So and then dA also to remind us that we are talking about the integration over areas, and so you can still recognize the heights versus multiplied by the areas of the bases. Later on, there will be dV here to whenever we're computing triple integral over volumes. So otherwise, it will be the same, and then we're not going to be talking about heights anymore because, well, that will be going in the fourth dimension. Okay, so that's just the notation. Once again, it is a limit of Riemann sums. And the plan of how to compute it, how to improve it, is right here. It's a little bit hard to actually carry out the whole thing because of the well, it's still Excel. It's really not meant for scientific computations, but it certainly can be done, and we'll do it in a minute. But first I want to do it at least once, a Riemann sum by hand with some elementary function. So, for example, which will be an approximation. So for example, f of xy is equal to x plus y, and we suppose over, say, a rectangle 0, 1, 0, 1. Okay, so this is what it looks like. My rectangle will be 0, 1, 0, 1. This one. Okay, and what is the graph of this function? X plus y, what's the graph?
It's a plane.
It's a plane, yeah, that was the question, that was the answer I was looking for. I mean, the function is linear, so the graph is a plane every single time. It is well, what it looks like. I mean, at 0 it is 0, so it will be rising somehow from the origin into the positive directions. Okay, so maybe like this. Okay, so it doesn't matter. The plan should work no matter what the picture is. The picture is meant to illustrate the definition doesn't really need any, and the computation doesn't really need any pictures. Okay, so I pick n is equal to 2, which makes 4 intervals, or 4 rectangles. Okay, so I cut this one into 2 and 2, like this. Okay, so the other responsibility of mine is to pick the endpoint, so this is already done. So let me write it out. X naught is equal to 0, x1 is equal to 1/2, and x2 is equal to 1. Same with y. Same with y over here on the y-axis. I have exactly the same thing. So these are the endpoints. So the endpoints of the intervals. And now, certainly you could, and they are on the x and y axis, so they are certainly, unlike in calculus 1, they cannot serve as sample points, because the sample points lie in the plane, so somehow, even if I want to use these, I will have to choose them, combine them, x's and y's. For example, I could choose lefting ends, both. Okay, so then what does it mean? It means that I will be, in each of the rectangles, I will be taking the bottom left corner as a sample point. Or as this sample point of this particular rectangle. Okay, so these are, I put them intentionally like this so that you can see where it belongs, how it belongs to which rectangle it belongs. And not that it matters a lot, but it just to make the point, because otherwise it could be anything else. Okay, so I list these. I could put them in a table, right? Just like they are here. I could probably easily put them in the form of a table. So f of, okay, let me list the points. It will be 0, 0, 1/2, 0, and 0, 1/2, and 1/2, 1/2. Okay, so these are my 4 sample points. Now I evaluate the function at these points, right? So the value of the function will be 1/2, 1, 1/2, and 0. So evaluate f, and that's what we get. Okay, so and then not forget to multiply by the areas. So delta A is delta x times delta y. In each case, it is 1/2. So delta y is delta A is 1/4. And so I just add the values of the function. Those 4, these are to be added together, multiplied by 1/4. Okay, so have my Riemann sum then is equal to, there is no particular order, right? So how about I go horizontally? So 0 times 1/4 plus 1/2 times 1/4 plus 1/2 times 1/4 and plus 1 times 1/4. Okay, so horizontally, and then next level also horizontal. Okay, so I certainly can finish the computation. 1/8 plus 1/8 plus 1/4, which is 1/2. Okay, so we certainly could ask ourselves if we are anywhere close to the truth, just like with the one-dimensional or two-dimensional rather geometric figures. So this one is to verify that would be a little work. So it's a plane going at 45 degrees away from the origin. So like this. So the green is the bottom, horizontal bottom. The blue is the slope roof, except it goes all the way to the ground. Okay, so I'm trying to think of what this is. So it's some kind of prism, and So like this, and the height, it goes up to 2, right? And these are 1s, the heights are 1. So can you tell me what the volume is? Well, think about it this way. That's what I'm thinking. Take 2 of these and put them one on top of the other with a twist. So I'll create another prism like that, and turn it upside down and put blue on top of blue. Okay, so and what does it produce? So I take this. I still have this, right? So this is short. This is not like this. And then there's another one on top of it. Hold on, I didn't do it.
So it makes it a square.
No, it's not a square, and not a cube. It will be elongated, right? It will be height of 2 with the base 1 by 1.
Okay.
Right, so it's 1, 1, and the height is 2, so it will be 2. The volume is 2. So, which means that the bottom of this one will be 1/2, right? Well, there you go. By coincidence, we got it right. It's actually not exactly a coincidence. Whenever we are computing integral of a linear function, then it is actually likely that some of the errors will cancel each other. Okay, like this. You probably have saw it in calculus 1. So if I take, say, I'm computing the area under this graph, and the function happens to be continuous, then well, if I do it this way, they certainly will cancel. Okay, so our estimation, underestimation, depending on your place. Yeah, well, no, we underestimated. I'm sorry. So why it actually? So the volume is 1, and I got it with 1/2. Why? Because this is the picture from calculus 1 that shows you underestimation. And it is a predictable amount of underestimation. If we picked the right hands over here instead of left hands, we would have overestimated. So anyway, one more time, probably worthwhile to carry out this one more time. So we computed the volume of a sphere, but it was a bit awkward because remember we had to delete those extra values because the Excel couldn't handle it. But if we go with something that with a complete domain, then with a whole rectangle domain, such as maybe a paraboloid. Okay, so then it should work out much better. So I'm gonna put here x squared plus y squared as we have in the past over here. So it is equal to. Hold on a second. Just want to take this one. Okay, so no square roots, just addition. And I need a plus here. Okay, so that is, you recognize the formula. This is the, what is it? It is a paraboloid of revolution, okay? And so I spread it out. Okay, a paraboloid of revolution, as you can see, it touches the floor, the XY plane at the bottom. Okay, so the function is defined everywhere, so there could be no trouble whatsoever in terms of the ability to compute it. And it is right here. This has been computed, as you can see, the total areas, the total number of values. So the heights are added together, and then they are multiplied by but 0.01 because the step in the x direction is 0.1, the y direction 0.1. So that's the formula you see at the top. That's how it works out. So the area is claimed to be 3. Let me do with this one, which is probably possible. Okay, and you realize that with desire, any kind of desire, we can approximate in this fashion the volume with any accuracy we want. Okay, we just make delta x smaller and smaller. We have to make the spreadsheet bigger and bigger, but at the end, the accuracy is entirely out. As long as functions are well behaved, continuous or ideally differentiable functions, there is no doubt that that will work out. Okay. Okay, so just like in calculus 1, properties of integrals, fortunately they all follow from, they first of all follow the ideas of calculus 1, but they also follow the properties of Riemann sums. Okay, so properties of Riemann sums. Do you remember any? By properties, I mean algebraic properties.
About the integral of f of x plus c of x?
Yeah, so the sum rule certainly could start with the integral because we already saw it, so let me write it out. AB f plus g dx in calculus 1 is equal to integral AB f dx plus integral AB g dx. Okay, so this is calculus 1. I want you also to notice that just in calculus 1, you reach this point and investigate these rules way before you confront it in the fundamental theory. Okay, which makes this an entirely different point, give you different point of view. This is entirely in terms of the Riemann sums, nothing else. So then if I want a similar statement for Riemann sums in dimension 2, I look at those Riemann sums. That's really not, it's not complicated, but it does look complicated, unfortunately. So it's this f of Sij plus g Sij delta A I from 1 to n, j from 1 to n. Okay, so that is my Riemann sum with n intervals and sample points pointing out there, and I'm taking the sum, right? I take the sum of the two functions, and now think about it. It is now, there's no limit, so we don't have to worry about that. It is simply a summation of, so it's, forget about those sigmas, have nothing to do with say series, for example. No, this is a finite sum. So I want to come up with a similar property for Riemann sums rather than jump straight to integrals, just in order to provide what amounts to a proof of this property. And I want you to see that there is really no challenge to recognize that how we can rearrange these terms the way we like, which just came up a minute ago. Well, think about it. So what this represents, it represents the heights of those bars with the bases are the same. Okay, so what can I do? I can expand. I can expand and just look simply expand, meaning multiply by delta A. So I'll keep this for now, and I have f Sij delta A plus f Sij g f Sij. Sij delta A. Okay, so then it becomes clear that each of these two terms are simply, it is two bars put one on top of the other. Okay, so imagine what happens to two functions when you add them. You add the values. If you add the values, you add the heights of those bars. You add heights of the bars, you add the volumes of the bars. Okay, so then these are volumes of the bars. And then, once again, the advantage is of Riemann sum is that summation is finite, so there is no limit there, and there are no issues of convergence. And so we can just redistribute things. And we have the same summation, but separate for f and g. G Sij delta A. Okay, and well, that's it. So the Riemann sum on left here is the Riemann sum of the sum, and this is the sum of Riemann sums of f and g. So Riemann sum of f plus g in the beginning, right there, this one. And now we have the sum of the two Riemann sums. So what remains is simply take the limit of the two if we want to have a property for the integral. Okay, so what happens? As n goes to infinity, what happens?
We approach the integral as a limit?
That's right, the integrals, the three integrals. The three integrals will be approached by, so this will be the same rectangle. In either case, it is in all three cases, all three integrals will be over R, except Riemann sum of the sum gives you the Riemann integral of the sum, dA. And then each of these terms give you the Riemann integral of the first one and the Riemann integral of the second one, of G. Okay? So that is where, according to the definition, that's what's in black is simply the definition of Riemann sums, and these are their limits. We assume that the default function is integrable. So, okay, these are the three limits. Now, what's the last step? What's the relation between the three? Well, the same relation as this, right? So there was a relation between the three Riemann sums. Now we have a relation between the three Riemann integrals. We have to just quote some statement to justify this from calculus 1. These are limits. Anybody remembers what the theorem we have to quote? We are talking about limits of sequences, and what we're saying here is that we're saying that the limit of the sum is equal to the sum of the limits. Okay, so what is it? It's the sum rule. Sum rule for limits. So every time it will come up every time whether you do a derivative, sum rule follows from the sum rule for limits. And for integrals, the same thing. You need the sum rule for limits in order to state the sum rule for integrals. Okay. All right.